Okay, I think it's me first on this slide deck. So
Yes, dear.
My name is Andy Weeks. I'm the Business Development Manager for SteerType, responsible for our computing business. Thank you all for taking time out of your schedule today. I have just 3-4 slides just to give you a brief overview of who we are, our partnership with Orolia, and how that's important to shape the solutions that we provide to our customers. Sophie, I think you might need to move on a couple of slides.
Sure.
Yeah, so actually probably, yeah, I think we've covered this. The people, yeah, that's us. Next slide. So SteerType, what we're about. So we're part of the Solid State PLC. We're a public listed company on the AIM. We're about 250 employees and the turnover of the group is about 60 million. SteerType is representing about half of that, and we are pretty much the engineering side of the business, and we're focusing on 3 technology areas coming out of 3 geographical locations. So computing and P&T products are coming out of our Redditch facility in Worcestershire. We have a power group based down in Crewkerne, down in Somerset. And then we have our communications, which is actually split into sort of 2 specific technologies. But within Leominster, we have our antenna group, where they actually have a big engineering facility. And the radio side is supported out of Redditch as well. So very much an engineering company at heart, as I mentioned. Within Leominster is our Centre of Excellence for testing, so we can do pre-compliance work for shock and vibration, temperature. They have a big RF facility for antenna design, but we as a wider group are working with a number of accredited test houses so we can deliver certified solutions to our complete customers. So harsh environments, we understand reliability, performance, longevity of supply are critical for all of our customers. And given that we work in industrial, military, government, oil and gas and medical markets, we understand the need to be compliant to DEF stands, MIL stands, Tempest, ATEX, and other regulatory standards that we need to have compliance. And the business has been around a long time, 80 plus years, since 1938, clearly not involved in the technologies that we talk about today, but it does have a long history of dealing with technology. Next slide, please, Sophie. So just covering briefly on the product areas. Within computing, we're very much focused on rack mount computers. So that might be industrial, military rack mounts. So COTS designs that can be easily customized cost effectively. So that might be branding, that might be fitting of third-party cards, that might be bespoke enclosures, it may be changing of I/O. So we find a lot of our customers like something off the shelf but tweaked to fit their needs. And the same is actually true for the fanless PCs. So a very good quality fanless computer, general purpose, with a bit of modification, we can get them to pass some MIL standards. We've actually got examples of using them in naval applications. HMIs, panel PCs, very broad range of COTS products. They may get used in car factories, or they could be used on a bridge of a deck, or they could be completely customized and bespoke designs as well. We also have some military grade computers, actual MOTS. So these might be low swap, high performance computers with 38999 type connectors on them. And we also have some rack mount computers that are already qualified to 461, 810, 59411 standards. We can also take care of full integration and certification of racks and transportation cases. And we've also got experience of Tempest as well. So that might be, again, rack mount fanless computers, HMIs, but increasingly we're doing high attenuation RF enclosures that allow people to fit standard COTS in there and still work within a Tempest type environment. Within our battery group, it's primarily focused on primary and rechargeable lithium packs, but we're not limited to those technologies. We also have experience and access to nickel metal hydride, nickel cadmium, and even some lead acid products. But really the skill here is taking standard cells, working with some of the world's leading cell manufacturers like Panasonic, LG, Electrochem, and designing and building packs to meet these specific needs of our customers. So typically these are going into high reliability applications like the oil and gas sector, medical, and increasingly actually unmanned autonomous devices that need to have large amounts of portable power. So the communication part of our business, antennas, they are in the development and manufacturing of high performance microwave and RF antennas. So they can range from 30 megahertz up to 60 gigahertz, and they'll be used in EW, spectrum management, ESR, RWR, and EMC applications. So they could be custom or bespoke designs, but typically things like spirals, horns, omnidirectionals, and we also get involved in reflectors and positioners, to name just a few. The other side of the comms group is the radios. So that's a MANA radio providing scalable, secure voice, video, and high bandwidth data networks. And typically these are being used to connect critical sensors and data sources in real time. And then lastly here we have the PNT element, which is obviously what you're here today to learn about. And I'll leave that to Orolia to cover more around their simulation, timing and positioning products. Next slide, please, Sophie. So this is an example of how these different technologies are integrated together within our customers. So clearly the product mix would look quite different depending on the application and the use case. So in a land or a surface ship or a subs environment, we would actually have a different blend of products to meet that particular requirement. But just running through this clockwise from the top, we have the data link, which is the radio element. We have one of our COTS, military mission computers, so a high performance computer that you can put a GPU in there. So increasingly we're seeing more virtualization requirements, more deep learning, more AI on the edge, sort of real-time type needs within these applications. We have a camera systems as well. We have what we call our crib system, which is a ground-based command and control, which is actually taking all of the elements of our business and putting it together. So it's taking the computing, it's taking the power, it's taking the antenna, the data link, and our engineering capability to make a finished product. So a good example there of the business putting together with all technology areas. Then we have the power pack, which can vary depending on the size and the weight and the density of power that's needed. There's a MIMO blade antenna there, but that could very easily be an EW antenna. That could be a spiral or omnidirectional. And then we have the resilient PNT piece, taking care of obviously positioning, timing, and navigation, which we'll touch on later on in the presentation. Next slide, please, Sophie. So this is the last slide I've got on my small deck here. So this is really just to show that we have a long legacy of experience within these sectors. It's very much core to our business. We're used to dealing with complex projects and can deliver those to Prince2 methodology. We're an IPC member, so it's really defining our quality standards for workmanship on soldering and cables, etc. And we're very active members of JOSCAR, ADS, Cyber Essentials as well. So we have security cleared individuals. We're used to handling sensitive information across our sites, and this is a sector that we've got a lot of experience in. And we understand our customers' challenges, and our aim is to help them achieve their goals through building trust through our experience, capability, quality, and working with world-class partners such as Orolia to help deliver an overall solution to our customers. So that was me, just a very brief introduction of who we are. If you have any questions about SteerTight, I know some of the people on the call know us as a customers, probably others don't. But if you have any queries or any other interest in some of the products that I've shown, then please feel free to contact me after the webinar. And on that note, I'll hand it over to Jeremy.
Okay, hope you can all hear me. Okay, thank you both. Okay, morning and welcome everybody. So it's Jeremy Thomas. I'm the business manager for Northern Europe and based here in the UK. Before we explore how to secure GNSS systems and protect against disruption, I'd like to take a few minutes just to introduce Orolia. Next slide, please, Sophie. Sophie? Okay. All right, thank you. Yes, Orolia is a group, as a group, is predominantly French, with our HQ in Les Ulis, that's in Paris. We have a US center in Washington, supporting much of our US-centric and government work. And while Orolia was incorporated in 2006, we have grown through 12 acquisitions since. Many of you will be familiar with some of our brands, such as Spectracom, McMurdo, Sabi, T4 Science, even new acquisition Skydel, and perhaps even some historic ones going back, such as Rapco here in the UK. These are all now within the Orolia group. Next slide, Sophie, please. So we have a global presence through a combination of our own core facilities and an established local partner network. Ones of note are our Paris HQ. This is actually two completely separate locations. There is our HQ facility and then also our secure facility for ADG work and special programs. Here in the UK, we have our Orolia Limited Portsmouth operation, as well as SteerTight, our partner also. Of note, Orolia Neuchâtel in Switzerland specializes in our space, maser and oscillator frequency technologies. And then in the US, our Rochester Core PNT facility, while in Canada, Montreal hosts much of our GNSS simulation development. Next slide, Sophie. So I'm going to run reasonably quickly through these ones. Okay, so about GNSS, might be brass tacks to some people, but just to go forward, it is a collective name for constellations of satellites, providing both accurate time and position data. You've got the big four global systems: Galileo over here in Europe, GPS from the US, GLONASS from Russia, Beidou from China. These are then supplemented by regional systems such as the Indian NAVIC and Japanese QZSS. GNSS use is increasing exponentially, so receivers are incorporated into more and more varied technology. New constellations are going up into space, as are new bands and frequencies coming online, L2, L2C, L5, for example, beyond the L1 traditional spectrum. The performance of GNSS is assessed through accuracy, integrity, continuity, and availability. So if we exclude for a moment some specialist signals like SASM and PRS, then GNSS remains at its core free to access, globally available, and accurate if used correctly. It's of great value to markets across commercial, industrial and government sectors. The European Space Agency, ESA, has stated that the GNSS receiver proliferation is anticipated to double again in the next 10 years from its late 2019 position. So GNSS is going nowhere. Okay. Next slide, Sophie, thank you. So what is the problem we are addressing? Essentially, GNSS use has exceeded its original design. From early US military uses, it was opened up in the 80s so that it now spans applications, both static or mobile, air, land and sea, unmanned and portable devices. Then there is critical infrastructure such as power grids, financial systems, broadcast and communications. GNSS today is fundamental to synchronizing operations and facilitating the timing and location awareness of many of the world's essential industries. And it's coped very well, but many of the applications were not previously considered, and so some of the deficiencies seen today are simply not accounted for. So GNSS signals, for all their use, remains a weaker signal and so susceptible to interference, jamming, and now even spoofing. Next slide, please. There have been many well-publicized spoofing and jamming incidents. These threats are real. Some examples, ongoing and publicised since November 2018, multiple Northern Nordic events coming from over the borders, often from well-known bases to the east. Planes and ground control are regularly interfered with, and there was another article just last week on the severity of these attacks. Another, and perhaps one of the most famous, was publicised back in June 2017. Here, a spoofing attack in the Black Sea, where a number of ships reported anomalies with their GPS-derived position, and found themselves all apparently located at an airport. Being so defined, it was a clear regional case of spoofing. Airports, coastlines and ports, government facilities and critical industries are targets. For those wanting to review this further, we have a whole resource section online where we log many of the public incidences. Ultimately, we need to find a solution to combat this problem. Okay, next slide, please. If we think about infrastructure and assets, they can have their GNSS challenged or even be in denied environments. For denied, you can think of tunnels, buildings, mountains, weather, and such like. We need to see the good signals, yet be able to survive if challenged. These can be intentional jamming or spoofing or unintentional interference. The RF world is a busy place and it's only getting busier. Either way, it's essential to understand the threats, put mitigating measures in place so we are prepared for all eventualities. Sophie, can you mute the mic? There's a bit of noise there. Next slide, please. Yeah, thank you. So the approach to resilient PNT. In the core, we have the GNSS receiver platforms. Integral to these will be oscillators for timing, and some will incorporate additional local sensors, such as inertial measurement units, commonly referred to as IMUs. Top left, for RF, understand GNSS and optimize its use and resiliency through interference detection and mitigation, IDM techniques. I will use this quite a few times today, so bear with me. Top right, on the network. So here we're talking about network timing, NTP, PTP, SYNC-E, White Rabbit, IP-based monitoring and control. The connection of integrated devices is proliferating, so protecting it, testing it, and certification are critical. And then at the bottom, here there is sensor fusion, as well as alternative signals of opportunity. So augmenting GNSS with other signals, be they terrestrial or space-based. So low Earth orbit satellites, ELORAN, pseudolites, SBAS, even local tachometers, compasses, and such like. Then finally, elements such as encryption and secure signals. All of these can be considered. Next slide, please. An important question to ask yourself for RPNT is, what do you want or what do you need to do? Okay, so we're taking a three-layer approach here. Detection. You want to be aware once you know that the primary reference is compromised. From a point of detection, you can then access an alternative or secondary PNT service. If you don't know this, and in detail, you cannot take action. Okay. Protection. You want to combat or reduce the threat. You may want to provide access to alternative PNT services that you do not currently have. Here you want to try and define the characteristics of this secondary service. Precision, stability, accuracy, traceability, maximum duration of the primary PNT service outage. All of these need to be considered. And then another most important part is data collection and/or analysis. You want to characterize, visualize, or document the threat. What is it? Where does it come from? Visualization through heat maps, monitoring of the quality of PNT service, recording, forensics in real time or over a period. Knowledge is power, as they say. Okay, so let's move on. Sophie, please. So let's take a look at PNT applications in their various domains. Next slide. Okay, so we'll start in space and work progressively downwards. So from space to aviation to terrestrial. We develop and build atomic clocks, many of the core elements in Switzerland at our Orolia Neuchâtel facility, ranging from the hydrogen masers. These were installed on the Galileo and Navic satellites, for example. So space-grade clocks, they can't go wrong. They need to have resiliency in themselves, and they've got to be accurate and maintain that for many tens of years. Okay, to space, then we've got space atomic rubidium references. Then on to aviation grade, rugged, low size, weight and power. Some would say swap PNT down to supporting the SATCOM ground segment with precision frequency references. And then finally onto mini rubidium clocks, which are small enough to be fitted into a portable device. Next slide, please. Then coming down, we've got air and land applications, UAVs, fighting vehicles, and their resilient PNT, helicopter and then soldier secure encrypted search and location beacons and their receiver systems. Then we've got C4I, incredibly important for what we're doing. So command, control, communications, computers and intelligence, its infrastructure and support. This means radar, this means SATCOMs, this means local links, this means wide area coordination and connectivity. All depend on reliable and very defined timing and frequency and combined PNT. Okay, next one. Then on to out to sea, naval and maritime. Orolia does a lot of work protecting both naval and maritime operations. Remote, often isolated entities, large and small, need to be resilient and self-aware. They are often away from more usual connections and links. So high value assets, it can be a container ship, an oil tanker, Coast Guard, frigates, or even ASVs now. These must all take precautions. So the need to understand and protect PNT with IDM techniques is paramount. Next one. And then finally, but no less important, is onto our transport, our cities, here where we are now, towns and national infrastructure. Haulage, rail, airports, financials, data centers, power grids, all must maintain accuracy, integrity, 24/7, 365. Some have additional requirements for traceability. So we see eCall, for example, in automotive, MiFID II for the banks and data centers, and e-commerce for PCI DSS, for example. All of these need traceable, reliable time and synchronization signals and some positioning. Smart systems are increasing their autonomy, their communication, their integration and cooperation, while requiring protection from malicious actors and what is around them. Okay, so we're ever connected world now. Okay, moving on. I'm going to come to the IDM part first, but first a brief on our core PNT platforms. These need to be resilient in themselves too. Next, please. On the embedded side, we have three principal resilient PNT platforms. Many of you will be familiar with some of these already, even actively operating them in some cases. So SecureSync for static, highly configurable time and frequency, synchronization and distribution. The VersaSync, essentially compact SecureSync package for mobile and harsh environments. And then the Versa PNT, taking the VersaSync and adding position and navigation capabilities. Don't worry, I won't talk about these for too long, but just a couple of slides on this. Next one. Okay, so for static timing applications, the SecureSync, a 1U rack mount primary reference clock, rugged to mil standard 810F, providing wide temperature, shock and vibration and such like. Multi-GNSS receiver, it's all in there. Cybersecure network management. Options for 5 oscillators for timing holdover, accuracy, and elements such as improved phase noise for communications. Multiple time and frequency references, GNSS, PTP, NTP, PPS, the oscillator. You can prioritize these and move from one to another through pre-configuration. Modularity, there's over 40 option cards available, making this the most customizable COTS solution out there. Now, while I say it's often for static applications, these are also used on larger mobile assets, and there is mobile and static mode capabilities here. We have rack capability, assets, with rack capability. So larger ships, trucks, and some aviation. Next slide, please. For smaller mobile timing applications, there's the VersaSync family. This packs all the capability of SecureSync into a very low size, weight, and power package. So multi-GNSS receiver, holdover oscillator choice again, DC power for vehicle and battery use. Ruggedization takes a similar approach to the SecureSync, now with mil standard 810G, and multiple time and frequency references and outputs. Many are now software defined, and through options, there is also hardware expansion. We even have options for program customization and sensor fusion. Okay. And then finally, for PNT applications, the Versa PNT. This adds inertial navigation sensors and Flex Fusion software to add navigation and positioning, even in GNSS denied environments. It also offers 6 degrees of freedom understanding on X, Y, and Z axis. Okay, so it's enough about the core platforms. So moving on now to the IDM side. Okay, next slide, please, Sophie. From before, we take that layered approach. Okay, so addressing the detection, the protection, the data collection and analysis. In the diagram, you start at the top for the over-the-air RF GNSS signal ingress point and come down through the antenna system and downlead to the receiver and platform itself. Then its software, its local references and other I/O. This morning, we're focusing on our IDM. By this, we mean the consideration of different antennae solutions, both active or passive, through IDM software, cybersecurity protection, and alternative signal considerations. All these can combine with already resilient core platforms to make an RP&T system. I must add that different combinations and configurations will suit different applications. That almost goes without saying. Next one, please, Sophie. First up, yes, the GPS dome. So this will be new to many people. The GPS dome is an active antennae system. It's a two-element SARPA antennae. So here we mean a controlled reception pattern antennae. It is the only commercially available non-ITAR anti-jam spoof SARPA system. Here we take a front-end approach in advance of the core platform. The dome rejects interference before it can even reach the receiver in the core platform. So features, so you've got SARPA null steering technology, and I'll come to that on a separate slide. You've got small form factor, less than the palm of your hand, 150 gram unit. It's easy to mount and use, especially in mobile applications. Minimal power consumption, less than 70.75 watts. And it's IP67 wide temperature, -40 to +85 for the harshest environments. This can be used in buildings still, up on masts, ships, UAVs, and aircraft. It's extremely versatile. Next slide, please. From a system overview point of view, and the core platform could be a secure sync or a Versa, it doesn't matter. But you have the inbound GNSS coming into two antennae systems. These can be standard L1 GPS antennas. You may have some of those already, some of ours, whatever. But you can also use with this our anti-jam AJ antennas even, and I'll come to those shortly. But these must be separated by a minimum of 25 centimeters where they're installed to be effective, to have this differential effect. Then into the GPS dome, processed, compared, and protected. And I'll come more into that on the next slide. And then onto the download elements into the core platform. Next slide, please. Right. So this all-important null steering algorithm. You can see these two antennas in the blue field and a jammer to the right. By having the two antennas, you can detect and analyze interference direction. So this comparative XYZ effect. Once received, we actively merge the patterns from the two antennas, and then we can also enable nulling of an interference from one direction. Okay, so one antenna and the computing behind it is coming back on the antenna that is in jeopardy. So patented architecture supports RF manipulation in real time. There's only a small 100 nanosecond constant delay in the RF chain in this system. Ultimately, it protects the core platform receiver while improving the ability to maintain a lock to signal. So there's that resiliency piece as well. Okay, next one, please, Sophie. Yeah, so the anti-jam AJ antenna, I mentioned it on the last section. So let's have a look at that. Yes, so many operators now even standardize on our AJ anti-jam passive antennas. Okay, so these are not active. They are still a GNSS antenna under the hood. However, and we're looking at the full range of GNSS L1, so including the big four plus some others. We also have, and we're now adding the capability to completely block the area of most susceptibility. And this is all packaged in a ruggedized IP67 enclosure. Okay, so let's run through that a little bit more. So from our tests and user base, it's been clear that the majority of threats to a GNSS antenna come from the horizon or below. Antennas are often up on masts, building roofs. And interference, whether intentional or unintentional, will come from the side or below in the majority of cases. The solution is to fully lock down and block the horizon with an RF mask and an intelligent head, and focus the truer reception upwards. And you can see an RF projection there in the bottom right. And it's effective to its purpose. Note, there is no detection or analysis here, but only as a protection measurement. So we've got a case example here, and some of the readouts from there are from further within the system. We've completed multiple tests. Here you can see an example. So over an 8-day period, you can see a staggering 90% drop on holdover events in a noisy, compromised environment. Holdover itself is hugely reduced from minutes to seconds. That means you're not going into alarm status all the time. Your engineers might not be being called out, etc. So alarms drop away to only a couple, which can be a big thing for remote data centers and the like. Ultimately, this saves engineering time and service, and we can provide more examples again within the presentation, which we'll share after. There are active links, and there's specific landing pages to some of these examples, jamming, spoofing cases, and the rest of it. Next slide, please, Sophie. Right, now on to the IDM software suite. So here with the IDM suite, we're now addressing all those 3 key points I mentioned right at the beginning. So detection, protection, and importantly now data collection and analysis and visualization. This will form a core part of Edward's demo. So I don't want to steal his thunder, so we'll see it in the flesh. So I'm only going to summarize here. Essentially, this is advanced software that can be unlocked and added to GNSS platforms, enhancing them for GNSS awareness. At its core, there are 75 algorithms. This software comes from security origins, government origins, and it will snoop the inbound GNSS and understand, visualize, report, and take actions when compromised. Slide, please. This works across all our core platforms, covering basic and advanced jamming and spoofing. For example, swept and pulsed carrier wave, chirps, noise variations, simulators, which could be seen as spoofers, data anomalies, jumps in position and time. All of these can be understood and protected against. So with the threat understood, notifications and alarms can go out. Fallback conditions can kick in, and that all-important analysis can then occur. And that can be in real time, that can be logging for future analysis. Okay. On. Now this really is in Edward's territory, so this is just for the sake of the slide deck afterwards, so I'm not going to cover this. Edward will be demoing this very shortly. Moving on. Right, that all-important cybersecurity. So we've dealt a lot with the RF environment and protecting that against the core platforms. Now onto the cyber side. Move on, please, Sophie. So I've talked us through the IDM, but the security, cybersecurity side is a huge topic. This could easily take up another session, but I wanted to say today it's just as much a consideration to protect the core platform locally and from its networking side. Cybersecurity means different things to different people. Worth noting that the SecureSync is the only Defense Information Systems Agency DISA approved timing and synchronization device for use in US DoD networks. So looking at some of the components of what cybersecurity make up, but not going into detail today, we're looking at things like networking. So there's access control list, ACLs, IP tables and firewall support. Login, we see this a lot in enterprise users, so LDAP, Radius, TACAX Plus. Password usage and how that's managed, so configurable passwords and policies for different engineering groups, password expiration, even HTTPS, things like NTP symmetric keys, auto keys, and then physical interface and ports. You can configure the onboard access keys and lock them out. You can even control the ports and lock those out as well. That would seem fairly basic, but obviously this is a hardened requirement for some. Again, we've got a link, we've got a landing page, so if you want to research that a little more and then come back to us, by all means. Okay, so we're near the end of my bit. I just want to really finish up on Orolia with Steatite and our unique value proposition. So we do have, by a long way, the broadest portfolio of resilient PNT technologies. This has been a focus for us. I would say about 70% of our business is in government area, which is absolutely critical for these types of technology. This is what we do. So field tested and active on military and government programs. I guess I've just mentioned that. Deployment in also, however, in commercial and critical infrastructure, things like stock exchanges and banks and cloud and data centers. These are high value assets globally needing support. We're there for them. Okay, these are mature and proven technologies. And we take that layered approach. We can take, a layered approach to design and customize solutions. So what you seek today can be customized. We can have program discussions. All these things are possible. And the last 2 points hopefully enhance that point. So we've got Orolia France and EU, secure facilities. We've got one in the US as well, completely separate from our commercial operations. And these allow us to handle sensitive, vulnerable data and classified technology and specialist programs. And here in the UK, this security clearance and strong industry expertise, as Andy said, with his company, Steatite. And with that, I think I'm done, and I'm going to pass over to you, Edward. Thank you.
Hello, everyone. Can you hear me? Sophie, can you hear me?
Yes.
Okay, perfect.
I
Thank
can
you
hear
very
you
much.
fine. Go ahead.
Yes.
So I'm Edward Bertolini. I am working within Orolia as an application engineer, and I'm working on the pre-sale side on the different product Jeremy introduced you just earlier. So today we are going to see a demo of the IDM software, which is the interference detection and mitigation software, which is embedded into our timing platform, the SecureSync. Can you? Thank you, Sophie. So before we get started into the actual demonstration, I wanted to go over the equipment setup that we have here. So first, I have a SecureSync that is running the IDM software. So the set of detection algorithm for jamming and spoofing we presented earlier. As Jeremy mentioned, we use over 75 algorithms checking different parts of the signal, different characteristics of the signal, of the GPS signal, in order to detect whether jamming or spoofing is present. So in this case, it is embedded into the SecureSync software. Then we have a combiner, which has one port connected to the LiveSky GNSS antenna, and the other port connected to a GSG, which is a GNSS signals generator, which is also known as a GPS simulator. In this case, we will use it as jamming and spoofing sources. So what we will do today during the demo is we'll add a jamming signal mixed with the LiveSky signal to mimic jamming. And we will do the same thing with spoofing. We will turn off the jamming and turn on the spoofing signal, and it will mix that with the LiveSky signal to feed into the SecureSync. And then we can observe, thanks to the IDM software, what is happening. So I'm going to take the control of the screen to show you my screen.
Should I need to stop mine, or do you just?
No, I think it will be okay. So can you see my screen?
Yep.
Yep.
Okay, perfect. So here we are on the web user interface of our SecureSync. This is the web user interface page when you log on to the unit, which is plugged on our network in our office. So we can see here on the home page the different reference available in the reference status. So we can see that the GNSS reference is valid and selected. The GNSS 0 reference is the first one, and it is valid, and we can see in the system status that it is the input reference used to define the internal oscillator of the unit. But we can see with that we have also other references that are listed in order of priority, meaning that if something goes wrong with the GNSS reference, the system will choose the next valid reference in the list. In our case, we can see that the second one is not valid, but the third one is valid. So if something goes wrong with the GNSS reference, we can expect the unit to rely on the third reference to discipline the internal oscillator. In case any other valid reference, in case we don't have any other valid references, this is the unit will go into what we call holdover, and will run on its own internal clock using the performances of the oscillator embedded into the unit to keep the timing as accurate as possible. So now if I go in the monitoring page, we will see the IGM suite page. Okay, so now I am on the IGM page. So looking at the IGM page within Secure Sync, we can see that the IGM here we are on the IGM dashboard. So the IGM just does the detection and it notifies the Secure Sync of that detection. And then the Secure Sync will choose to invalidate the compromised GNSS reference if some jamming or spoofing is detected. So here, this is the default view. On the left, we see some status and settings option, and the dashboard takes up the rest of the window. So first, we will cover the dashboard. This is where the most of the important operational data is displayed. So starting with the graph on the top left here, we see the system state. This graph represents the cumulative penalty score for jamming and spoofing. So the black line in the middle is a critical line, here, this one. And when jamming or spoofing scores breach this line, the IGM software considers the environment jammed or spoofed. So in the banner at the top of the dashboard, for now it is green, but it will turn yellow for jamming or red for spoofing. We can differentiate between jamming and spoofing by looking at the color of the line that we have here. So on the system state, so we will see when I will enable some jamming or spoofing signal. So right now we don't have any spoofing or jamming. There are some events that can occur during the day that will trigger some of the algorithm, and you might see a little spike, but as long as this is within the normal range, everything is still fine. That's why we really use a scoring system where it has to be multiple things that are filling the algorithm, or one thing that waved very highly so that the lines the line goes above the critical line, and that's when jamming or spoofing will be detected. Moving to the top right of the window, we see the number of SVs used graph. This graph plots the number of satellite vehicles the receiver is using. Below this graph is the carrier to noise graph. It depicts the average signal strength from the tracked SVs for the internal receiver. And at the bottom is the GNSS spectrum. So this is a 16 megahertz wide representative spectrum centered around the GPS L1 frequency. This is not a raw RF spectrum, but this spectrum is just representative based on the output of the receiver. It is not a spectrum analyzer, so you can see some spikes, but it is just the way the data are interpreted. You can't measure the power with the spectrum, but you can see the type of waveform present if it is strong enough. So all graph can be viewed in a variety of time windows by clicking on tabs under the dashboard banner. So here we have the 1 hour time, but we can also see what happens during the last 3 hours, the last 6 hours, 12 hours, day, the last 3 days, and just the last week. Okay, so first now we will do some jamming. So the first thing we will do here is adding a jamming signal. So I have a jamming signal set up that I'm going to add to the secure sync. So I'm going to enable my jamming signal. Okay, start. So to generate the jamming signal, as I mentioned, I am using the GNSS signals generator we can also provide. So I am injecting a swept signals. Sorry, I'm injecting a swept signals, a swept frequency signal, and it mimics a chirp jammer. So we can see in this case that I have a swept frequency signal, and right away this is a pretty strong jamming signal. So our score went way up, and it detected the jamming very quickly. So it turned orange on the banner, on the dashboard banner. So it means that the features detected the jamming, which is occurring. So now if we go back on the reference page, so the home page of our timing units, we will see that we can see that the status of the GNSS reference is invalid now, and our unit switched to another reference, which was valid. So in our case, it is the third reference. The NTP is the next reference considered as valid, and which can be used by the units to discipline the internal filter. So we can see in the system status on the left side that now our current reference is the NTP reference. So we can see that our unit is still in sync here. In the status, it is still in sync, but we have a fault because of the IGM critical alarm. But because of the critical alarm caused by the IGM feature. So now we are currently in sync with another reference, and this for now we are in tracking setup because it is this new reference is displaying the internal oscillator. So if I remove, if we go back on the broadshield on the IGM feature, sorry, on the dashboard, now we can see still the strong jamming signal, and I will remove my jamming signal for you to see what's also happening. So when I take the jamming signal away, we wait a few minutes for a few cycles of good live GPS, and we will see that the indication will fall down below the critical level. So you can see it's already falling down, and we can already see on the spectrum that the jamming signal has gone away. So now we can see that the IGM feature, once the jamming level will be below, okay, now the jamming level is below the critical line, so we can see that the IGM features has detected that everything is okay again. The jamming level has gone below the line, and if we go back in the reference page, we will see that the GNSS reference is considered as valid again by our timing platform. So let's go back once again in the home page where the different references are. So here in our case, we can see that the GNSS is now valid again with the two green LEDs, and in the system status on the left side, we can see that the reference used by the system to discipline its internal oscillator is the GNSS once again. So now I will do quite the same exercise with some spoofing signals. So let's go back in the IGM dashboard, and on my GNSS signals generator, I will now select spoofing signals. So here everything is back to normal. And there is no jamming or no spoofing detected. So I'm going to turn on our spoofing signal. So my spoofing signal is sync on NTP to inject some signals which are very close to the live signals. So we have to wait until the next minute so that the spoofing signal will be launched. Okay, so we'll see in a few seconds the jamming increasing on the detection software. Okay, so now my on my side the jamming signals is on, and we can see on the dashboard of the IGM software that some jamming event is detected, but also some spoofing events you will see. Yeah, the refresh rate is not very quick here. I'm doing everything remotely from my home, so my network is not very perfect. So for now, the system is detecting some jamming, and it should detect some spoofing. Oh, I don't know if I'm still connected. Sophie, can you hear me?
Yes, I can hear you.
Oh, okay.
Sorry.
Because I had a network
Oh, sorry.
connection message.
Can still see your screen and it's moving, so that's the good news.
I will turn off and turn on my signals. I don't know what happened. Are the curves moving on your side?
Not anymore. No, now it is. Yeah.
Okay, so I am sorry, I launched the wrong scenario. So I am launching once again that time a spoofing signal, not a jamming signal. Sorry. So we can see on the GNSS spectrum some level modification, and if we wait a few seconds or minutes on the system state, we will see some jamming detection, spoofing detection. Sorry. So for now, it's detected as a jamming signal because the signal sent from the GNSS simulator is quite strong. But I did the test just earlier, and we had some jamming curves also. And as you can see on the previous hours or days, yes, we detected some also some spoofing thanks to our different test setup. So if you go back on the reference page, same as earlier, the GNSS is considered as invalid by the system because of the IDM detection, which notifies the secure sync that the GNSS input is compromised, and then the systems choose to select another reference to define its internal oscillator. So if I go back on the monitoring side.
We're nearly up to time, Edward, and we probably want a few minutes of closing out. So
okay, I think you can take the following step, Jeremy.
Can we go back on the presentation then?
Yeah, let's.
Yes, I won't go through all the menu if we don't have time enough.
That's fine. Okay. Just a few closing comments, really, and obviously Q&A. Thank you, Edward.
So now, there you go.
Yeah, so just one last slide from me. A lot of this wouldn't be possible, understanding part of P&T without our simulation side of things. You've seen it today, a part of it in action with Edward's demo, but it's safe to say we're a leader in the simulation field. So we've got our well-established 5 and 6 series. We've got our newer GSG 8, which really is taking you up to some of the highest applications, and most high dynamic aircraft, UAVs, other types of assets, type signal simulation and test. Here you can do multi-reference, all frequencies, all bands, all constellation, jamming and spoofing testing within these units. If you want to get really involved, we can do anechoic chamber testing, SARPA antennae testing, and into SARPA antennae testing. So we've got a full range on the simulation side. What we'd like to ask is any feedback from you as to whether you would like to see the next webinar being about simulators. We would truly welcome that. It's a thought to do another one of these if it's well received. And from that, we'll just open the floor to some Q&A. Don't know, Sophie, did we get anything on the chat? We've got a few minutes, and we're happy to stay for a little while longer. If anyone does have any questions, they're happy to share, or even feedback would be great. Obviously, it's if you prefer to use emails or phone us or whatever later, that's also amazing. But does anyone have any questions?
Hello, Jeremy.
Hello.
Hi there. Sorry, I couldn't see the slides on my poor internet connection, but I just wanted to thank you for the webinar. It's very interesting.
Oh, pleasure from all of us. Yes, it's been good. Thank you. I mean, given the audience, I wasn't expecting that many public questions, if I'm honest. But we'll give it a minute. But like I say, get in touch with Andy, get in touch with me, email, phone, however you want to do it. We would welcome any feedback on the simulator webinar as the next one. That could be a really exciting topic. I'd be pleased to do that. Otherwise, we will shortly close out. All right, Sophie, I think we're there.
Yes, sorry. So for the people who are still online, so obviously you are going to receive the presentation shortly, as well as a questionnaire indicating what Jeremy has been talking about. So the potential new webinar on testing and simulation, as well as your comments and follow-up question you may have on this session. Thank you for your time.
Thank you.
Thank you. Thanks very much.
Thank you.
Thank you very much.
Thank you. Thanks a lot. Thank you.
Thanks.